faithfully delivering value, interpreting great books from around the world. Hello, this is Sally's Book Talk. Today, I'm interpreting the book Decoding the Universe, subtitled A New Information Science Perspective on All Things. In today's era, it's an information age. In most people's understanding, information is an abstract concept. It could be a piece of news, a string of numbers, an article, or a list of names. But these are just a small aspect of information. It encompasses far more than that. Um, in fact, every electron, every atom, every cell in the universe is filled with information. Information theory describes all life on Earth, and even the physical structure of the entire universe. Thermodynamics, relativity, quantum mechanics, it's all a form of information theory. So, to speak, information shapes the universe. This book reinterprets all things in the cosmos from an information perspective and conveys a core message to us. The universe might just be a giant information processing computer. The author of this book, Charles Seif, is a science writer. He has a master's in mathematics from Yale University and is a professor in the journalism department at New York University. His expertise in mathematics, combined with his fluid writing style in journalism, makes the most bizarre and incredible fields of physics clear and transparent. Next, I'll interpret this book for you from two aspects. First, what is information? Second, what impact does information theory have on the field of physics? First, what is information? In 1948, a 32-year-old engineer and mathematician discovered an important feature of information. It can be measured and quantified. This was an epoch-making realization and the foundation of information theory. This young mathematician was none other than Shannon, the founder of information theory. Maybe you haven't heard of Shannon, but you must have heard of bit. That term was created by Shannon. Bit is actually the basic unit of information measurement. When Shannon created information theory using bits, his starting point was surprisingly simple. In his view, the essence of information is question and answer. In daily life, we encounter many binary choice questions. For example, are you male or female? Is the light on or off? Should we take the train or the plane? And so on. To answer such questions, we can use two symbols like 0 and 1, using these digits to represent yes or no, true or false, red light or green light, etc. 0 and 1 can answer all binary choice questions. The set of answers made up of zeros and ones is binary digits. Each digit represents one bit. To answer a binary choice question, you need one bit of information. So if the question is a bit more complex, say when answering a four-choice question, does that mean we need 4 bits? For example, imagine you're a spy gathering enemy intel. You learn the enemy will choose one transportation method: car, train, ship, or plane. Now you need to use signal lights to convey this information. How would you do it? How to represent these 4 options? First method, prepare 4 lights. 1 light for car, 2 for train, 3 for ship, and 4 for plane. This approach is straightforward but rather cumbersome. But there's a smarter second method. Use just 2 lights with green filters to show either red or green light. Then we can represent it this way. Red for car, red-green for train, green-red for ship, green-green for plane. Pretty clever, huh? For a question with 4 answers, 2 lights each making a red or green choice completely solves it. This equals 2 binary decisions, just 2 bits needed. Similarly, for 8 possibilities, 3 lights, 3 bits can distinguish all options, and so forth. No matter how complex the choices or how many possibilities, if they're finite, we can answer with a bit string. You might have played this game. Think of a number between 1 and 1,000. I only need 10 yes or no questions to deduce your number. Like, is it over 500? No. Then is it over 250? No. With proper questioning, I'll get it in under 10 tries. Each yes or no gives one bit, reducing uncertainty. Distinguishing 1,000 possibilities takes just 10 bits. Far fewer than you'd guess, right? Shannon found that for impossible outcomes, bits needed equals log 2 of n. Meaning with x bits, you distinguish two possible outcomes. This formula is revolutionary. The number of atoms in the universe is finite, only about 10 to the 80. We can pick any atom in the entire cosmos, and using this formula, we can calculate how many bits are needed to identify it. The calculation result is guaranteed to amaze you. Pinpointing an atom across the entire universe requires only 266 bits. However, not everything in life is multiple choice. We often face open-ended questions. For example, if I ask you what the capital of France is, such a question, can it also be answered with bits? The answer is absolutely yes. The capital of France is Paris, which in French is Paris. In the French word, it can be treated as a series of yes or no questions. For instance, there are 26 English letters. To locate any specific letter, it's equivalent to screening within a range of 1 to 26 using binary questions. According to the earlier formula, it takes 5 questions, so each letter can be encoded with 5 bits. Since Paris has 5 letters, spelling out this word requires a 25-bit string. To put it plainly, all information, all questions with finite answers can be expressed with bit strings made of zeros and ones. That summarizes the core idea of information theory. Information has evolved from an abstract concept into a physical entity. In computers, it's these simple strings of zeros and ones that construct today's highly complex information society. Information theory has pioneered an entirely new scientific domain, truly a groundbreaking innovation in human cognition. But this isn't the full extent of information theory's contributions. Information theory is so powerful because of its deep connection to the physical world. It has far surpassed its original scope. Shannon's initial conception has ignited a genuine revolution across all realms of physics. Next, we'll cover the second part. What impact does information theory have on physics? Here we'll discuss 3 perplexing paradoxes in physics, and the key to resolving them lies precisely in information theory. The first area is classical physics. Within classical physics, there is a branch called thermodynamics, which has 3 fundamental laws. Here we'll focus on the second law of thermodynamics. It states that in a closed system, without external energy input, disorder and randomness only increase, never decrease. For example, mixing cold and hot water results in lukewarm water. It won't remain half cold and half hot. This measure of disorder is called entropy. Hence, this law is also known as the entropy increase law. And this law can be said to be one of the most unassailable laws in physics. Yet Maxwell, the great scientist who discovered electromagnetic theory, conjured up a demon for this law, punching a huge hole in the second law of thermodynamics. Maxwell proposed this thought experiment. A box filled with gas contains a frictionless valve. Closing the valve divides the container in 2. Inside the box is a demon that manipulates the valve to separate hot and cold atoms. For example, when a cold atom approaches from the left, the demon opens the valve to let it move right. When a hot atom comes from the left, the demon closes the valve to block it. This keeps one side cold and the other hot, reversing entropy without energy cost since the valve is frictionless. This paradox is called Maxwell's demon. Whether human or machine, if ever created, it could reduce entropy without energy, rendering the second law powerless over cosmic order. This problem puzzled scientists for years until information theory unveiled its demon-slaying sword. First step in exorcism. Since the demon separates atoms with the valve, it must first determine whether an atom is cold or hot. That means it must measure atoms and extract information that doesn't come free. Processing information always carries an energy cost. In this sealed, pitch-black system, if the demon expends no energy, just staring blankly, it can't distinguish hot or cold atoms, let alone separate them. Next comes step 2. Imagine the demon as a computer programmed to open or close valves. It first measures atomic temperature, writes a 1-bit measurement record on disk, then executes commands to open-close valves based on that record. Information theory states, information is physical. Computer storage is finite. When full, it must delete files to free space. During deletion, it releases energy to the environment, generating more entropy. So the demon can't reduce entropy without paying a price. First, it has to acquire information, then store it, and finally delete it. All these information processing steps come at a cost. Either the demon consumes its own energy or it increases entropy. Information theory defeats Maxwell's demon, defends thermodynamics, and moves beyond classical physics. Now we move to the second major field of physics, relativity. Einstein's special relativity is one of the foundations of modern physics, and it tells us that observing the same object from different perspectives often yields different answers. For example, for an object moving at high speed, its time slows down, length contracts, and mass increases. Like the second law of thermodynamics, special relativity is considered a perfect theory. But what physicists find even more thrilling than building a perfect theory is breaking one. Special relativity also faces tests and doubts from all sides, with the most troublesome being the barn pole paradox. Imagine an athlete holding a 15-meter-long javelin running towards a 15-meter-long barn. This barn has a front door and a back door, both equipped with sensors. When the javelin fully enters the front door automatically closes and the back door opens simultaneously. Now, what happens when the athlete runs towards the barn at 80% of the speed of light? According to special relativity, the length of a fast-moving object contracts. The athlete himself and a stationary observer will experience completely different scenes. In the athlete's eyes, he's running at 80% light speed, so the barn is rushing towards him at 80% light speed. From the athlete's perspective, the high-speed barn contracts from 15 meters to 9 meters. Since the javelin was longer than the barn, before it fully passes through the front door, the tip will bang into the back door. To a stationary observer, the barn remains unchanged, and it's the fast-moving javelin that contracts to 9 meters. When the javelin is fully inside the barn, the front door closes, the back door opens, but the tip is still 6 meters from the back door, so the athlete runs out without any hindrance. Great, now we've caught Einstein's weak point. For the same event, one sees a collision, the other doesn't. Special relativity seems contradictory. If you find it confusing, you can check the diagram in the audiobook notes. Now, information theory is about to shine again. This paradox overlooks a crucial premise of special relativity. Information cannot travel faster than light. This is exactly the key weapon to resolve the paradox. The barn's front sensor must send information to the back door to trigger its opening. Information is physical, and transmission takes time. To a stationary observer, after the contracted 9-meter javelin enters, the front door closes while sending an open signal to the back that the javelin tip is already 9 meters ahead, racing forward at 80% light speed, essentially competing with the information, and leading by 9 meters, the tip hits the door before the information arrives. No matter how the javelin's length or speed changes, since information can't outpace light, it'll never beat the tip, meaning the back door never receives the signal. The observer also hears the bang, aligning both perspectives. This light speed limit theoretically eliminates the paradox. But does it hold in reality? Experiments show superluminal light waves exist. Can't they transmit information? The answer is actually no. Scientists tested this. Superluminal pulses carried 1 bit, right equals 1, dark equals 0, while regular light carried another, comparing transmission speeds. But results showed the opposite. Though regular light was slower, detectors received its information first. Superluminal pulses suffered distortion. Detectors always needed extra time to decode the information. Even if photons travel faster than light, information propagation never exceeds light speed. If superluminal pulses are like airplanes, the information they carry is like checked luggage. The plane may land first, but luggage takes forever on the conveyor belt. Special relativity stands firm. After special relativity, let's examine quantum mechanics, which with relativity forms modern physics' twin pillars. Quanta are the most fundamental building blocks of matter, or rather, the most basic carriers of energy. All microscopic particles, including atoms, electrons, and photons, are manifestations of quanta. The quantum world has a bizarre feature called superposition. In our everyday world, an object can only be in one state, like a cat that's either alive or dead. But in the quantum world, a particle can exist in countless states simultaneously, realizing all possibilities. If we use a quantum to transmit information, it's simultaneously both 1 and 0. This eerie phenomenon is quantum superposition. Though this superposition effect is baffling, it has been observed repeatedly in the tiny quantum world. Truly an undeniable phenomenon. But why can't the macroscopic world have such superposition states? After all, the macroscopic world is built from countless microscopic quanta. To address this, Austrian physicist Schrödinger, one of quantum mechanics' founders, designed a famous thought experiment, introducing another troublesome paradox to physics. This paradox is the renowned Schrödinger's cat. We can reinterpret this experiment through the lens of information theory. In a box, there's a cat and a vial of poison with an information receiver attached to the poison. We then fire an electron into the box. This electron has two paths. One is a dead end where nothing happens if taken. We label this path as 0. The other path leads to the poison's receiver. When the device detects the electron, it automatically releases the poison. A kitten in the box dies instantly. We label this outcome as 1. So what actually happens inside the box? According to superposition, the electron takes both paths simultaneously. 0 and 1 occur at once. Thus, the poison is both released and not released. The kitten is both alive and dead. How can a macroscopic being be simultaneously deceased and living? And even more bizarrely, this superposition persists as long as nobody opens the box. The moment someone opens the box to observe the cat, it instantly collapses into one state. Be alive or dead, it seems the act of extracting information kills the cat, making information not poison, the fatal trigger. This cat that's both dead and alive has been puzzling physicists. The key to solving this paradox is still information. We just talked about quantum superposition states. They're most afraid of being observed, afraid of being measured. So it's not that the act of observation itself changes the superposition state. Rather, observation brings about the transfer of information. When an atom is observed, photons or other particles must collide with it, disturbing its superposition state. At the same time, the colliding particle gains information about the atom. This flow of information from the atom to the environment causes the superposition state to collapse. So if the cat's box is never opened and no one observes whether it's alive or dead, would the cat really be in a superposition state of both dead and alive? Don't worry, the cat's fate was decided long ago. Even if humans don't observe it, there are other observers. This mysterious observer constantly watches all things in the universe, gathering their information and spreading it into the environment. That observer is nature itself. Nature is constantly performing measurements, and this is key to resolving the Schrödinger's cat paradox. Our Earth is bathed in photons from the sun. When a solar photon hits a leaf and reflects into our eyes, we see the leaf. But regardless of whether our retinas receive this information, The leaf's information exists out there. Sunlight shining on the leaf is actually a form of natural measurement. When wind rustles the leaves, it's gas molecules in the air colliding with them to create sound waves, also spreading the leaf's information into the environment. Photons and air particles are nature's detectors. We're just receiving the information already stored in those particles. If we extinguish the sun and all stars, leaving no photons in the universe, it still wouldn't stop nature's measurements. Space is full of cosmic rays and neutrinos. They too pass through that leaf and reflect back, with information still flowing into the environment. If we completely isolate this leaf from the whole universe, locking it in a vacuum box at absolute zero, what would happen then? According to quantum weirdness vacuum fluctuation effect, particles and antiparticles can constantly pop into existence out of nothing in a vacuum. So to shield an object completely from nature's measurements is impossible. Research shows that larger, looser, and hotter objects leak information to their environment faster. This is the fundamental difference between the microscopic quantum world and the macroscopic classical world. So for a tiny atom, obtaining its information is harder, so its superposition state lasts longer. And as long as it remains undisturbed by other particles, it happily stays in superposition. But a cat is different. It contains billions of atoms, being both massive and warm. It experiences countless particle collisions with the environment. Long before humans open the box, nature has already measured the cat. The cat's information has long scattered into the environment. It chose life or death long ago. We can never capture a cat in superposition. This explains Schrodinger's cat. This cat no longer has to be both dead and alive. Information theory tells us there's no fundamental difference between the macro and micro worlds. Their apparent differences stem from how nature acquires and disseminates information. The universe's diverse phenomena result from information flowing everywhere. From these three paradoxes, we see how information theory has remarkably repaired and refined the three major physics domains. These fundamental laws of physics are essentially laws about information. We can boldly predict, perhaps information is the supreme law of the universe, and that's not an exaggeration. To this day, our exploration of the universe still holds many unsolved mysteries. Take Schrodinger's cat. An electron in superposition randomly chooses a state when observed. So where does the other state go? This question sparks debate about the multiverse, one of the ultimate topics in exploring cosmic structure. The key still lies in information theory, which offers one of the strongest explanations for the multiverse. David Deutsch, one of quantum computing's founders, said the multiverse's structure is determined by information flow. Information shapes our universe like an onion with layered membranes, each layer an independent universe where electrons choose different paths. As long as these two cosmic membranes remain pressed together, the electron appears to exist in two places simultaneously. That's superposition. When we observe the electron and extract information from it, we peel apart these two membranes. Observers on the membranes also split. People in each cosmic membrane only see the electron's path in their own universe. Throughout the book, the author maintains this view. The universe itself is a vast information processor. Information shapes the entire cosmos, flowing endlessly like an unceasing stream. Since the universe is a computer, it too will experience component aging and eventually reach its computational limits. Physicists calculate this cosmic supercomputer has performed 10 to the 20th power operations since its birth. Its work is about halfway done. After executing the remaining 100 to the 120 operations, all life in the observable universe will go extinct. Our information will scatter across a lifeless cosmos, becoming utterly worthless. This is information theory. It may unlock the universe's ultimate mysteries, yet also harbors seeds of final destruction. Perhaps this is precisely the power of information as the supreme cosmic law. All right, that concludes our interpretation of Decoding the Universe. You'll find listening notes below the audio. See you tomorrow.